So welcome back again to our second recorded session. This one is probably going to be a little bit of a puzzle for you right at the very beginning, because we are, after all, here studying biology. And one of the things that always puzzles freshman students, whether they're taking a biology class for majors, for science majors, or in the case of this class, a biology class for non-science majors. One of the questions that always puzzles them is, why do we have to do so much chemistry? After all, we're here to study biology. Why chemistry? Well, the answer can be summarized relatively easily by just saying something that I said in our first recording, that a cell is essentially a sac full of water in which chemical reactions occur. And the reason why a cell does what it does, or a multicellular organism made up of many cells working together does what it does, is on the basis of those chemical reactions. It really is not only that simple, but that complicated, because it is simple to understand the concept of a cell as being a bunch of chemical reactions, but trying to come to terms with all of that chemistry, that's hugely complicated. And that is way beyond the scope of this class, trying to come to real terms with the complexity of cellular chemistry. That being said, however, we cannot avoid talking about some chemistry. There's really no way of getting around the fact that in a biology class, you really do need to discuss some chemistry. So in this chapter and in a couple of following chapters, we are going to focus quite a bit on chemistry, because it helps us understand some of the very essential processes that we're going to talk about in two chapters, the chapter on cell respiration and the chapter on photosynthesis, because those are very, very important biochemical processes, the source of energy for life's use in the form of photosynthesis, and the way life goes about processing the molecules that are formed during photosynthesis as a storage of energy to make that energy available for cellular use. That would be cell respiration. We do cell respiration first and follow up with photosynthesis, but essentially the two processes go hand in hand, and they're all chemistry. They're all very much chemistry. So we really do need to ease ourselves into an understanding of chemistry in order to be able to make sense of everything. So in this chapter, we're going to talk a lot about basic chemistry. And I'm hoping that for some of you at least, this is just a review of something that you've already studied in the past. If it's new to you, don't panic. If you've avoided chemistry for the whole of your high school career, don't panic. This is not going to be a chemistry class, but it is going to cover some chemistry. And some of it, even if you've stayed away from chemistry, even if you've taken only a few science courses and not really taken a chemistry course before, much of this, or at least some of it, you will have heard about before, because it's talked about a lot in elementary school science and middle school science, and to some degree in high school. Well, if you took high school biology, it will have been covered, possibly at the same level that we're going to cover it here. But you should have heard some of this already. I mean, should not all be mysterious. But some of the things that we're going to talk about may be some things that you haven't heard of before. Don't panic. Well, I'm not expecting you to be chemists. I'm not expecting you to be biochemists. All I'm asking you to do is to make sure that you take the time necessary to come to terms with the chemistry that we are going to cover in this chapter, because we are going to build on this in upcoming chapters. And it's going to be very important that you remember what we've talked about in this chapter, because we're going to build on that. So, well, having said all of that, let's get started on taking a look at some basic chemical ideas that we need to understand in order to be able to understand cells at their most fundamental level. So we begin by looking at something that at first glance may not seem to have much connection with chemistry at all. The notion of radioactivity. And we know that when we hear the term radioactivity or radioactive, we tend to be a little nervous about this because we have learnt over time that radiation is damaging. The irony here is that while radiation can be damaging, it does damage DNA. We know this for sure, and it can create changes in the DNA, mutations that can lead to cells becoming cancerous. And radiation comes in all types of and forms, and we'll talk a little bit more about that when we actually do the photosynthesis section, because we do focus on a type of radiation because light is a type of radiation. Believe it or not, what we talk about in terms of radiation has a connection to light and some other forms of energy. But we'll get more into that when we talk about photosynthesis. But when we hear the term radiation, we hear the term radioactivity, we get all nervous. We might get worried that something is going wrong. But the irony is that radiation can not only cause cancer through mutation, but used correctly can also cure cancer, because moderate damage to cells and moderate damage to DNA can create mutations that lead to cells becoming cancerous. But if you hit them with a high dose of radiation, you actually kill those cells. So it's really all about exposure and how you go about utilizing the radiation energy. It can be harmful, but it can also be beneficial. But the bigger question is, where does that radioactivity come from? Because in reality, and this is going to sound a little bit scary, we are surrounded by radiation all of our lives. And in fact, some of the atoms that make up your body are themselves radioactive. And before you go running, screaming, I'm radioactive, it's going to kill me, the low level of radiation that's present in your body is something that your body can tolerate. In fact, it has mechanisms to handle that radiation and to repair any damage that may occur because of the presence of that natural radiation. We have evolved in the presence of that radiation, and as a consequence, over time, we've developed mechanisms for dealing with it. Otherwise, we wouldn't have been able to survive, and life itself would not have survived without being able to adapt to the presence of that low-level natural radiation. Where we get into real trouble with radioactivity is when we get exposed to higher levels of radiation on a regular basis. Then it starts to become dangerous. And that's why we try and avoid any exposure that is above normal background levels. So when you get an X-ray, they'll cover you with a lead apron to protect you from the X-rays, because X-rays are a form of radiation. If there is the potential for exposure to radioactive elements, and we'll talk about a couple of those a little bit later in the chapter, then we do procedures to try and reduce the level of those radioactive materials. And if we find that places have become contaminated with radioactive material for any reason, then we'll go to great lengths to make sure that we reduce that contamination to undetectable levels by cleaning, by digging things up and carrying them away, storing them effectively in places. But of course, we also know that periodically accidents happen. So we have Chernobyl, we have 3 Mile Island in Pennsylvania where radiation got released. We've got Fukushima in Japan where radiation got released. And we know that there have been issues with this released radiation. We see increases in levels of cancer. Whole regions have been roped off and people are not allowed to live there anymore because it's considered to be too dangerous. You can visit temporarily, but you've got to come out again, and you've got to take all sorts of precautions when you do. because we are worried about overexposure to radiation. We're always being exposed to radiation. It's the level of exposure that becomes the important thing. And it's all about making sure that we reduce our exposures to just that natural level of radiation, not to expose ourselves to higher levels. But we still haven't answered the question, where does this radiation come from? That's something that we are going to address as we start exploring the chemical nature of life, because it turns out that we can explain the presence of radioactive materials by understanding some basic chemistry. So let's go and explore some of this basic chemistry to explain where this radiation comes from. And I've talked about all of these ideas in these slides. If you want to read about these slides, download the presentation from the link in the task list, and you can read these slides at your leisure. So the first thing that we need to recognize is that the universe that we can see and touch and taste and manipulate, what we often refer to as the visible universe, is made up of matter. And matter is something that has two very important inherent properties. That is, if you have matter, you have something that has these two properties. You can't separate matter from these two properties. Number one is that it occupies space, or it has volume. And that's pretty obvious when we look around us. The second thing is that it has mass. This may not be as obvious because we often confuse the term mass and weight as meaning the same thing. And they don't necessarily have to mean the same thing. Now, here on Earth, your mass and your weight are the same thing, because your weight is a product of the Earth's gravity pulling on your mass, and that's what gives you the weight that you have. But if I was to say, put you in a rocket and take you to the moon, you would still occupy the same volume, and therefore we could conclude you have the same mass. But your weight would be 1/6 of what it is now. So if you were the ideal human being, well, let's say you weighed 180 pounds. Let's not say the ideal human being. You'd say you weighed 180 pounds here on Earth. We sent you to the moon, where your mass remains the same. The volume of your body doesn't change when you go to the moon. But if you're standing on the moon and we put you on a scale to measure your weight, you'll find that your weight has gone from 180 pounds down to 30 pounds. It's instant weight loss. But nothing has really changed about the amount of matter that's in your body. If you want the most extreme example of that, we could take you to the space station, the International Space Station, the ISS. And there you would be considered to be weightless. That's what we talk about when we talk about the astronauts being on the space station. And the reason for that is that while they are being pulled on by the Earth's gravity, the movement of the space station around the Earth offsets the pull of gravity, cancels out the pull of gravity, so that in fact there is no perceived weight. You are weightless because the two forces are being cancel each other out. But again, the size of your body hasn't changed. The inherent mass that your body contains has not changed. It's just that the force of gravity has changed. So these are the two inherent properties of matter. They occupy space, or they have volume. It has volume, and it has mass. And it comes in three forms that we are familiar with here on Earth: solid, liquid, and gas. When we start looking at matter, what we discover is that as we subdivide it into smaller and smaller and smaller units, we find that ultimately all matter breaks down to a series of units that we refer to as elements. And the elements are composed of small units called atoms. And by definition, an atom is the smallest unit of an element that has all the properties of that element. So what do I mean by that? Well, if I was to take an aluminum can and start slicing and dicing it up into smaller and smaller and smaller units, ultimately I would get down to something that is the smallest unit that has all the chemical properties of aluminum. And when I get to that point, what I have is an atom of aluminum. An atom then is the smallest unit of an element that has all the chemical properties of that element. So as soon as we start recognizing that matter is made up of these elements, the next thing is to try and figure out how many elements are there. And that can be a little bit confusing because we have to differentiate between what is referred to as naturally occurring elements, those that occur naturally in nature, and those that are man-made, because yes, we do have the capacity to be able to make elements that don't actually occur here naturally on Earth. So when we start doing this, we start thinking in terms of the periodic table, because the periodic table lists all of the elements that we know of, both those that are naturally occurring and those that are man-made. So what I want to do is move the text box out of the way a little bit so we can see all of the bars. Let me put it over here in the periodic table so that we can see what we're looking at here. So you may or may not recognize some of the symbols on here, but each one of these symbols, each one of these boxes represents an element. Of all of these elements, 92 are considered to be naturally occurring. And those are all the elements that extend down to this one, uranium. Uranium is the largest naturally occurring element on Earth. And as far as we know, probably in the universe as well. Although that may not be necessarily the case, because it's been said by Einstein, and who's going to argue with him, that the universe is not only weird, it's probably weirder than we can imagine. So it's even possible that some of these man-made elements actually occur naturally elsewhere in the universe. So from uranium onwards, so it's these ones in these boxes, plus these ones, because if you look at where these two rows slot in, they slot in where this line occurs. So these ones are all artificial, these ones are all artificial. And so when we think in terms of the naturally occurring elements, it's from element number 1, hydrogen, through to element number 92, uranium. Now you'll notice that each of them has a number. Hydrogen is number 1, helium is number 2, lithium is number 3, beryllium is number 4, boron 5, carbon 6, da 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 da. The list goes on and on and on. And we've got things like gold, which is Ag, silver, which is Au, mercury, which is Ag, chromium, Cr, manganese, Mn, zinc, Zn, copper, Cu, nickel, and so on. Sometimes the letters match the actual common name of the element. Sometimes the letters are related to what is referred to as its Latin name. The names that were given to these elements back in the early part of the development of chemistry, when it was still considered to be a pseudoscience called alchemy, where people were trying to convert elements that were common and unremarkable into elements that were more rare and much more valuable by carrying out chemical manipulations. We now know that that's not possible, but that's what the alchemists were trying to do. And gold, Ag, was the gold standard. Yeah, no pun intended there. But this was what everyone was trying to make, gold, because it's valuable. It has very real value. But you could see that gold does not have a letter designation that relates to the name gold. But that's because the Latin name for gold was, let me go back a slide because I may have it actually back here. No, I didn't put the name in, and I forget what the name is now. But the AG letters come from, AG letter designation comes from the Latin name. So each element has a name, has a symbol, it has a number, and the number is usually placed on the periodic table as a superscript adjacent to the letter. Or in this case, they put it above the letter in the box. Below the letter is another number, or as a subscript is another set of numbers. And these also relate to a chemical property of the atom. So the superscript, what is referred to as the atomic number, is equal to the number of protons, positively charged particles that exist in the nucleus of an atom. And hopefully you remember all of this from some previous class. The bottom number is referred to as the atomic mass, and this is the total mass, or as it would be here on Earth, the atomic weight, because they're equivalent here on Earth, of the atom. And this is not measured in any unit that you would be familiar with, because the units of mass or the units of weight that we are familiar with simply won't work for atoms. They're way too big and atoms are far too small. So the atomic mass or atomic weight is measured in a unit called Daltons. And it's given the symbol Da. So let me fire up the pen, change the color to black. So measured in Daltons, that's the unit. And the symbol is uppercase D, lowercase a. So we will possibly not use that again. We may talk about that a little bit as we go through some of the later material in this chapter. But I'm just putting that in there so that you know what this is all about. There's no harm in actually adding in a little bit of extra information. The more you know, the better you're able to explain things, so it never hurts to know a little bit more. So as we go through the table and we think of hydrogen as element number 1, that also tells us that it's got 1 proton in the nucleus, because the atomic number is equal to the number of protons. And so hydrogen as element number 1 has 1 proton, and all atoms of hydrogen have 1 proton. It defines the element. So let me put that in here. So the number of protons, or atomic number, defines the element. So if you're looking at atoms of hydrogen, they'll all have 1 proton, because the atomic number and the number of protons is the same number. So hydrogen element number 1, 1 proton. Helium element number 2, 2 protons. Lithium element number 3, 3 protons. Beryllium element number 4, 4 protons, and so on, till we get to uranium element number 92, and as you might guess, 92 protons. So the atomic number and the number of protons, same number. The atomic number tells you the number of protons. The atomic mass also tells you some information, because there is a second particle, and this is included in an upcoming slide. There's a second particle that's found in the nucleus called a neutron. And neutrons have approximately the same mass as protons. And so when we think in terms of the mass of an atom, we think in terms of the number of protons plus the number of neutrons, because they're both approximately the same mass, and they contribute the greatest amount to the mass. In fact, they contribute all of what we take into account when we think in terms of mass of atoms. It's the number of protons plus the number of neutrons. The reason why we don't include the third particle, and of course you're aware that the third particle in an atom is an electron, is because electrons are so small and contain so little mass that even for uranium, the amount of mass from the number of electrons doesn't amount to anything. It amounts to less than 0.1 of 1% of the total mass of an atom. So we don't even consider the mass of electrons. They don't have enough mass to count. So we just simply don't think about it. The mass of an atom is strictly the number of protons plus the number of neutrons. So we don't actually give an actual number when we have the element information in a periodic table for the number of neutrons, but we can figure it out because we look at the mass, we look at the number of protons, and the difference between the two, in other words, subtract one from the other, tells us how many neutrons are present. So if the mass of carbon is 12 and the number of protons is 6, the difference is obviously 6. So carbon typically has 6 neutrons plus 6 protons for a total mass of 12. And so you can figure out all of this by simply understanding the information that's available in the periodic table. It tells you all of this. But what I've just told you is a very simplistic view of atoms because it gets a little bit more complicated than that. And we really do have to address that complexity a little bit because it helps us understand or to answer the question that we posed in the opening slides of the chapter. Where does radiation come from? Where do radioactive elements come from? Because it's in understanding this added little bit of complexity about atoms that tells us where the radiation comes from. So we'll address that in a minute, but before we get to that, one of the things that is important for us to understand as we delve into the chemistry is that while there may be 92 naturally occurring elements here on Earth, not all of them will we find in living organisms. In fact, there are only 25 elements that are commonly found in organisms. And of those 25, only 4 of them need to be considered in order to take into account over 96% of all the atoms in your body. And these are the 4: oxygen, hydrogen, carbon, and nitrogen. And typically it's oxygen listed first, hydrogen listed second, carbon listed third, nitrogen listed fourth in terms of percentage. I'm not sure why they put them in this order, but oxygen is usually number 1. Hydrogen is listed number 2, carbon number 3, nitrogen number 4. So why oxygen and hydrogen? Well, easy to understand this one. Found in water. And because these are the elements that make up water, and water constitutes about 70% of your body, not surprisingly, hydrogen and oxygen are the most commonly found elements in an organism. Then carbon, I'm going to bring an arrow down on this one. So carbon forms the skeletons of the remaining 30%. It's organic molecules. And we'll be talking about these in the next chapter, the organic molecules and the role of carbon. And then nitrogen is the 4th element because I think that's readable. I don't think it's too cramped. But what we will find in the next chapter when we start talking about carbon and we start talking about organic molecules is that nitrogen, along with hydrogen and oxygen in different combinations, are attached to the carbon skeletons to form the different types of organic molecules. So that's why nitrogen is included in this list as element number 4 in the list. So it's fairly easy to explain why these elements make up 96% of our body. So when we start looking at it here, and I think this is percentage by mass rather than percentage by actual number of atoms. And that may be why hydrogen and carbon have been flipped on this list, because this is in terms of mass of the element versus number of atoms. Because in terms of number of atoms, there are more hydrogen atoms than there are carbon atoms. But it doesn't really matter. It's still the same 4, irrespective of how we list them. Then you'll notice that of the remaining 4%, about 3.7%, I think it is made up of this list of elements. Calcium, because of the bones, phosphorus, because of bones and the nucleic acids, DNA and RNA, potassium found in lots of cells, it's good for nerve cells particularly, sulfur found in proteins, sodium also found in cells in small amounts, very useful for nerve cells as well in combination with potassium. Chlorine is useful in some cell activity. Magnesium, because of its role in helping enzymes regulate chemical reactions. We'll talk more about that in another chapter. And then the remaining missing little bit is made up of these elements called trace elements. These we only need very, very small amounts. And what is really important to understand about these is that in very small amounts, the trace elements are really beneficial. But in larger amounts, many of these are actually toxic. So copper's toxic, cobalt's toxic, chromium's toxic, tin is toxic, zinc is toxic, iodine is toxic, selenium is toxic, molybdenum is toxic in too much, in large amounts. That's why these are referred to as trace elements. We need small, small, small amounts of them. We do need them. They're absolutely essential for the proper behavior of cell chemistry. They're absolutely required, but only in really small amounts, hence the term trace element. These are considered to be minor nutrients or minor elements. So let me put so required in some amount, but not required in the huge amounts of as in terms of oxygen, carbon, hydrogen, and nitrogen. So this is the basic chemical makeup of our body. If we were going to dig really deeply into the chemistry, as we would if this was a biology majors class or a chemistry class, we would focus mostly on carbon, oxygen, hydrogen, and nitrogen because they are the elements that compose most of your body, most of living organisms. But we're not going to dig really deeply into it, into the chemistry. So all you need to be aware of right now is that these 4 elements compose the vast majority of the body. There are other elements, minor nutrients, and there are reasons for those. And then we have the trace elements that need to be present, but only in really, really, really small amounts. Otherwise, they tend to become toxic. So when we start thinking in terms of where the elements are going to turn up, we find that they start to form substances, or they're present in substances. If the elements are present in combinations with very fixed ratios that we can write out as chemical formulas, then we refer to them as compounds. So here are two compounds that you have no doubt heard about. Table salt, which is sodium chloride, and it is made up of combinations of sodium and chlorine in a ratio of 1:1. But there's no such thing as a sodium chloride molecule, which you'll understand why by the time we're done with this presentation this morning. Another compound is water. Why? Because every water molecule has 2 hydrogens and 1 oxygen. That's the ratio of hydrogen to oxygen. And there is a reason why they did get together in that particular ratio, and we'll address a little bit of that as we work our way through this presentation. But these are compounds, they're both substances and compounds, because the ratio of the atoms present in these substances is constant. All water molecules have 2 hydrogens plus an oxygen. All table salt accumulations, or table salt crystals, if you want, have lots of sodiums and lots of chlorines, but the ratio of sodium to chlorine is always 1:1. It's an invariant ratio. So we consider these to be compounds because the ratio of the atoms remains constant wherever you look at these. So I've given you some of this information already. An atom is the smallest unit of matter that still has all the chemical properties of the element. I've talked a little bit about the particles that are found in atoms. The proton is in the nucleus, it has a positive charge. The neutron is in the nucleus, it has no charge. The electron, that's where it gets a little bit confusing as to where the electrons are located. Most people would say they circulate or they orbit around in the space around the outside of the nucleus, and that is technically correct or functionally correct, but it's way more complicated than that. We're not going to get into the details. Okay, we don't need to address the complications of that. But if you're using this class as a stepping stone to taking the General Biology 1 class, the first of the 2 biology classes for majors, you will dig much deeper into the structure of an atom, and you'll dig very deeply into where the electrons are actually located, because it is an important part of your understanding at that level to know the nature of where the electrons actually are, because it's the behavior of the electrons determine what goes on in chemical reactions, and we need to dig a whole lot deeper into that in those more advanced biology classes, so we would get into it. But in this class, we're not going to dig very deeply into it because it's not necessary. So what is important about the number of protons? Already mentioned, it is the atomic number. It defines the element. The number of protons plus the number of neutrons gives us the atomic mass. So how do we figure out the number of electrons? Well, that is simply the same number as the number of protons, because atoms in their normal state are electrically neutral. And the only way to be electrically neutral is to have the same number of positive charges and negative charges. So if we know the number of protons in the nucleus, which we always do because it's the atomic number, then we automatically also know the number of electrons, because the 2 must be the same in an electrically neutral atom. And then we can figure out the number of neutrons by simply taking the atomic mass, which we can always find from the periodic table, and subtract from that the atomic number, the number of protons. And whatever's left is the number of neutrons. So this would be a typical way of drawing an atom. And this is actually a drawing of the element helium. So helium has 2 protons. It is element number 2. So there they are. Helium atoms have a mass of 4. So that tells us 4 minus 2 equals 2, that there must be 2 neutrons in the nucleus. Because there are 2 protons, there are also 2 electrons, and they circulate in a 3-dimensional volume of space shaped like a sphere. But if we were drawing the atom in 2 dimensions, we would typically draw it as a circle, and we would put dots on there to represent the 2 electrons. It is way, way more complicated than that. But again, we're not going to delve into that complexity. All I require you to know at this point is that the electrons circulate in a 3-dimensional volume of space around the outside of the nucleus. So let me put this in. And it's spherical. So while we're not going, as I said, we're not going to dig deeply into this, I've added a little bit of extra information that is not talked about a lot in the textbook, but I think this is kind of important for you to know because you may have heard something about this. There are multiple energy shells. Helium just happens to have electrons in the first energy shell, which is closest to the nucleus. But there are multiple energy shells in a concentric set. So there's shells inside shells inside shells inside shells. And if you think about, if you've ever seen one of those Russian dolls where there's a doll inside a doll inside a doll inside a doll, that's pretty much what we're looking at here. So the innermost one is the smallest 3-dimensional volume. And then as we move away and we look at each of the subsequent dolls or energy shells, as we move away from the innermost one, they get bigger and bigger, and they occupy more space. And as they occupy more space, they can also be occupied by more electrons. And so as the atoms get larger and have more protons in the nucleus, there is more space for the accompanying electrons, because remember, the number of protons tells us also the number of electrons. And so as we move to larger and larger atoms, as we move through the periodic table and we start to consider larger and larger atoms, we also find that there are more energy shells, and each subsequent new energy shell is larger and can hold more electrons. And so there is always going to be 3-dimensional volumes of space in these energy shells to hold the electrons. We're not going to get into the details of that. That's just a little bit of extra information that you might find useful. You may have even heard it before already. So again, not telling you anything new here. I've already introduced some of these ideas to you, but it's helpful to hear it again. The atomic number is the number of protons. The atomic mass is the number of protons plus neutrons. So we can figure out we can always figure out the number of protons and the number of neutrons, because we always have the atomic number of protons. We also always have the mass number, which is the protons plus the neutrons. So neutrons is the atomic mass minus the number of protons, or the atomic number. Now, one of the things that we have noticed, one of the things that we notice is that all atoms of an element have the same mass. And the extra mass so if it's got extra mass or less mass, that can't be due to changing the number of protons. Because if you change the number of protons, you've changed the element. Remember, the number of protons in the nucleus defines the element. So if we're talking carbon, carbon is element number 6, and so there must be 6 protons in the nucleus. So carbon is element 6. So all carbon atoms must have 6 protons. Oops, we'll do it correctly. Carbon 12, carbon 13, and carbon 14. But they're all carbon, so their atomic number must be 6, but their mass is different. So we can't change the number of protons. So it has to be the neutrons that are changing. Can't be the electrons because they don't amount to much. So carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. And carbon 14 has 6 protons and 8 neutrons. And the name that we give to these different types of atoms is isotope. So the different types of, or the different forms of carbon atoms are the isotopes of carbon. Do it this way. There you go. So isotopes are simply different forms of atoms based on their mass. So carbon 12, which is the most common form of carbon, has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. Carbon 14 has 6 protons and 8 neutrons. And carbon 14, as a consequence, is also extremely radioactive. And some of the carbon in your body is actually carbon-14. Because carbon-14 is a naturally occurring isotope. It's part of the complement of carbon that we find here on the planet. And if we consume carbon, which we do, because carbon is a constituent of all the organic molecules that make up our food, then we are going to be taking in some carbon-14. And as we'll see at the end of the presentation, the presence of that carbon-14 can actually be a useful tool biologically for many reasons, but you'll see why. I'll show you a specific example why when we get to the end of the presentation. But again, remember, this is naturally occurring radiation. This is not something that we need to panic about. Our bodies can handle that natural low level of radioactivity. And many of the elements, in fact, the vast majority of elements do have at least one isotope that is radioactive. There are a couple of elements, lead is the one that is most notable, where all of the isotopes of lead are non-radioactive. But a large number of elements have at least one isotope that is radioactive. Where do the isotopes come from? By having different numbers of different numbers of neutrons in the nucleus. That's where the mass difference comes from. So this spells out again what is meant by an isotope. So here's the carbon example. Carbon-12, 6 protons and 6 neutrons. Carbon-13, 6 protons and 7 neutrons. Carbon-14, 6 protons and 8 neutrons. And this is the one that is radioactive. So maybe I'll just put a note in here. As I said, that can be used, that's a very useful tool later on when we get to the end of the presentation. So one of the things that we know about radioactive isotopes is that they break down. And they break down by giving off the radiation. I mean, the fact that the radiation exists is the evidence that the radioactive isotopes are breaking down, because they give off the radiation as part of the breakdown process. Their nucleus is unstable, and the nucleus breaks down and expels radiation or gives off radiation as part of the breakdown. And so if you get exposed to a lot of radiation, it can be a problem. But remember again, unlike, and I want to stress this, so let me put this in red. So the natural low-level radiation, again, remember, not harmful. It's only when you get exposed to high levels of radiation that are above the normal background levels. So here is an example where you might get exposed to a higher level of radiation. There is a gas called radon. It is, and the isotopes of, or an element called radon, the isotopes of which are radioactive. And radon is given off by rocks. And where this can become a real problem is if you have a basement in your house that goes down into the rocks. Because the rocks can give off radon, and radon can accumulate as a gas in the atmosphere of the basement, and you're breathing that in. And it is a cause of lung cancer because it can cause mutations in the lung cells. And under normal circumstances, you would not expect to be exposed to radon. But if you have a basement that has a rocky formation, you can get exposed to radon. Where you may also get exposed to radon is from a concrete lining of a basement, because concrete contains natural rock, and if that natural rock contains a high level of radon, it can be released into the atmosphere of a basement as well. It is possible to test for radon. This is something that is done on a regular basis, particularly up in the Northeast, where basements are and the Midwest, where basements are a standard part of a house. Radon testing is one of those things that is always required as part of buying and selling a house where this is a problem. Here in Florida, we don't have basements, and we don't have the sort of rocky formations that would support the development of a basement, and therefore run the risk of radon exposure. It's typically here in Florida, we're not typically at risk of exposure to radon. It's more of a problem up in the Northeast and the Midwest, where you have basements dug into the basement rock, or you have a finished basement with a lot of concrete that has the potential of outgassing radon as well. There, the testing is routinely done on a very regular basis. In fact, you can get a home kit for testing for radon. I don't know how accurate those are, but it is possible to get kits to actually test for radon in a basement. So this is a radioactive isotope that is a potential source of mutation and therefore potential source for cancer. Now, because it is the electrons that are associated with an atom that determine chemical reactivity, it turns out that the radioactive isotopes behave in much the same way as the non-radioactive isotopes in chemical reactions. And this makes radioactive isotopes very useful, because given that they give off energy, you can tell exactly where they are. And because they behave chemically just like non-radioactive elements, if you introduce small amounts of radioactive isotopes, you can track chemical reactions by seeing where the radioactive isotopes go, because they're following the same path as their non-radioactive cousins. And so a lot of the chemistry that we'll be talking about this semester in terms of respiration and photosynthesis, those were figured out by following carbon-14, the radioactive isotope of carbon. It behaves chemically just like carbon-12, the most common form. And so it allowed the researchers to figure out the chemical reactions involved in cell respiration and photosynthesis by seeing where the carbon went by following the carbon-14. And there are a number of different types of radioactive isotopes that are used in medicine, what is called nuclear medicine or radionuclide. Yeah, try saying that really quickly. And you'll see that your tongue gets twisted up in knots trying to say it. But the use of radioactive isotopes in modern medicine is very important, because they are very important diagnostic tools. And so there are a number of different medical tests that are done by using very, very low concentrations of radioactive isotopes that disappear from the body really quickly within the space of 24 hours to make sure that your total exposure time is really short and the amount of extra radiation that you're exposed to is incredibly low, to the point where it's not considered to be dangerous at all. And I've had a couple of studies done that have used radioactive isotopes as tracers to basically look at the function of my heart. That's what it was being used for, just to take a look at the function of my heart and make sure that I did not have any preliminary evidence of heart disease or anything like that. I've got pictures that show that my heart is in perfect working order and that the blood flows through it just fine, thank you very much. But it was done with some radioactive isotope tracers that allowed the doctors to see how well the blood was flowing through the arteries in my heart. So these are the sorts of things that we can do. And in some cases, the use of radioactive isotopes has meant that the testing is more accurate and safer because it doesn't involve introducing all sorts of pieces of equipment into the body that could potentially trigger the very thing that you're trying to avoid, something like a heart attack or a stroke. The use of the isotopes means that it's non-invasive, non-life-threatening as a consequence. So, time for our first break. We've been going for a little while now. So here are our first concept check questions. So the first is, of the 25 elements that are found in most organisms, only 4 account for 96% of the atoms. What are these 4 and why are they the most abundant? And the second, all the oxygen atoms have how many protons? And what varies when we're talking about isotopes? Let me pause here. You may pause the recording, but I'm going to come back and answer the questions in a few seconds. So if you took an actual break, or if you pause the recording so that you could think about these questions before coming back and hearing the answers, welcome back. So of the 25 elements that are found in most organisms, what are the 4 that account for 96% of the atoms? Hydrogen, oxygen, carbon, and nitrogen. Why are they the most abundant? Well, hydrogen and oxygen, because they make up water, and water is 70% of an average organism in terms of the molecules present. Carbon, because carbon forms the skeletal structures of the remaining 30% of the molecules that are not water. And then nitrogen, because in combination with oxygen and hydrogen, it also is attached to the carbon skeletons to make up the different types of organic molecules that cells are composed of. We'll talk about those in the next chapter. All oxygen atoms have 8 protons because oxygen is element number 8. But the number of neutrons can vary between the isotopes. Remember, again, if you change the number of protons, you're actually physically changing the element, because all atoms of an element have exactly the same number of protons. Only the neutrons can vary from isotope to isotope. So, with the exception of a very small number of elements or atoms that exist on the far right-hand side of the periodic table that are known as inert gases or inert elements, all the atoms of the other elements wanted to combine in combinations that help them look like those inert gases. In other words, make them chemically unreactive. All elements want to reach a point where they are chemically unreactive. And the advantage for the inert gases is that they are already chemically unreactive because of the electrons in the energy shell that is, and I'm trying to avoid getting into too much detail, but perhaps I really do need to get into some detail. So remember I said that there were multiple energy shells or electron shells that the electrons could occupy. If you look at the atoms of each element, there is an outermost energy shell or electron shell that has electrons in it. And that outermost energy shell is called the valence shell. It's called the valence shell. having a full valence shell. Makes it chemically unreactive. And so the inert gases are like this. And the other elements are going to get together to either physically exchange electrons or to share electrons in such a way that it looks like they have a completed valence shell. That's the reason why atoms interact with each other. So the idea here is to consider the number of electrons in the valence shell and think about how the atoms can go about satisfying the requirement of having a full valence shell. It could be as simple as giving up an electron. It could be as simple as gaining an extra electron. In some cases, it becomes a little bit more complicated and they actually wind up sharing electrons in order to be able to reach this inert form. But that's basically what the atoms are trying to do. Reach this inert form by exchanging electrons, by gaining an electron, giving up an electron, or by sharing pairs of electrons. And that leads us to thinking about chemical bonds. What they're doing, what the atoms are doing in terms of giving up electrons, gaining electrons, or sharing electrons determines the type of chemical bond that they're going to form as they interact with each other. So the first type of chemical bond is called an ionic bond. And an ion is simply an atom or a molecule that has either lost an electron or gained an electron and therefore become charged, either positively charged or negatively charged. So loss of an electron results in a positive charge. Gain of an electron, as you might guess, results in a negative charge. And so you have positive ions and negative ions. So the attraction between the positive and negative ion is ionic bond. So the ionic bond is simply the electrical attraction between these two oppositely charged ions. And so the ionic compound or ionic substance that you're most familiar with is table salt, otherwise known as sodium chloride. It's a type of salt. I mean, I know we refer to it as salt, but really it's an example of a larger group of chemical substances or chemical compounds called salts. And salts are ionic substances because they're made up of oppositely charged ions. So here is a short video that shows you how sodium and chlorine go about forming an ionic bond. And in essence, what happens is that the sodium gives up its electron to chlorine, because chlorine has room for 8 electrons. So it gives up this one electron, and the chlorine then gains an electron. The sodium now has lost its electron, and this shell, this next shell in with 8 electrons in it, now becomes the shell that it exposes to the world. This is its valence shell, and it has 8 electrons in it, which means it is actually full under the terms of what full means here. And so sodium has a complete valence shell. Chlorine now has a complete valence shell. But in the exchange of electrons, sodium now becomes positively charged. Chlorine now becomes negatively charged, and the electrical attraction between the two ions means that they are now bound to each other by this electrical attraction, and that forms the ionic bond. And I'll make sure that this video and all of the animation and all of these animations that are here in the PowerPoint are available in the resource section if they're not already there. They should be there, but if they're not, I'll make sure that they're there. And you can go and take a look at these. You can also download the PowerPoint slides, but it's in a PDF document, so you won't actually be able to run the animations. You'll have to get those from the resource section, or you can go to the study section in Mastering Biology. So if you've never been to the study section yet, the study area as it's called, now might be a good time to go and take a look. So all of the animations that you're going to see here are included in the study area. So it might not be a bad idea to go and take a look at those, but as I said, I'll make sure that these are available in the resource section as well. So this animation walks you through the formation of an ionic bond and shows you the exchange of electrons and how that results in an ionic bond. The next type of bond is called a covalent bond, and the name actually tells you what's going on here. So co means to share. And valent means valence shell. So a covalent bond is a shared pair of valence shell electrons. One from each atom. And that's the important part. The two electrons that are being shared, one of each pair must come from each of the atoms. So one atom provides one electron, the other atom provides the second electron that's going to be shared. And these are the chemical bonds that are present in molecules. So when we talk about atoms forming molecules, they do so by sharing these pairs of electrons to form covalent bonds. So this animation shows you how these two hydrogen atoms get together to share their electrons. They share these two electrons together in a combined space so that each of the two atoms sees these two electrons. And as far as they're concerned, each atom sees those two electrons, and because it's the first energy shell that's involved here, which only can never contain two electrons, they see the two electrons, they are satisfied. And so that shared pair of electrons forms the covalent bond, between the two hydrogens. So this animation shows you the nature of a covalent bond. And whenever the atoms are the same, from the same element, they're going to form a covalent bond that's referred to as non-polar. The two ends of the bonds are exactly the same. There's no distinction between the ends of the covalent bond. So we refer to this as a non-polar covalent bond. But it turns out that the sharing does not necessarily always have to be equal. So think about it this way. This is the example that I always use because it seems to resonate with everybody. I don't know whether you have brothers and sisters, but if you do, and you've ever had your mother come out, say with a candy bar, and she said, here, share this. You know that the sharing is likely to take place, but you also know very well that it's probably not going to be equal sharing. That if you are the youngest, you're probably not going to get much of a share because your older brothers and sisters will get more. It's just the way life is. Unless your family is unusual, you know that that's just the way life is. Of course, if you're on the other end of the relationship, you also know that that's the way life is. If you're the older brother or sister, you take the bigger share. It's just the way life is, particularly when we're very young. That's the way we operate. And so in some cases where atoms have to share electrons to form covalent bonds, while they share, they don't necessarily share equally. And so when we have this unequal sharing, which I will show you in the next slide, as far as the water molecule is concerned, oxygen is the older sibling, hydrogen is the younger sibling. And what effect does that have? Well, it means that at the oxygen end of the covalent bond, there is a weak negative charge, which we represent by this little squiggle, which is actually the lower Greek letter delta. Think of it as being equivalent to our lowercase d. And so at this end of this covalent bond, there's a very weak negative charge. At this end, at the hydrogen end, there's a very weak positive charge. And the reason why is because the pair of electrons that are shared here are being shared, but they're not being shared equally. Oxygen gets the greater share than hydrogen. Likewise, for this covalent bond, there's a partial negative charge there, and there's a partial positive charge here. So let me put a note in here. So as a consequence of this slight offset of the electrons towards the oxygen, giving them the partial, giving that end of the covalent bonds a partial negative charge, the result at the hydrogen end is to leave behind a small or partial positive charge. And these covalent bonds, I didn't want to do that. I know sometimes I can get it back if I'm lucky with the redo. To keep it here. So there it is. Let me just bring it back up again. So we were in luck, I kept it. Set this now in red. Back to black. So these are called polar covalent bonds. Why? Because there are opposite charge to each end of the bonds. They have poles, a positive pole and a negative pole. As a consequence of this offset or this unequal sharing of the electrons. And so water is sometimes described as, or is described as, a polar molecule because it has these opposite charges at each end of the covalent bonds. We have these polar covalent bonds. And so again, you can take a look at this animation because it'll walk you through the formation of these polar covalent bonds, and you'll find this animation again in the study area. And I'll make sure that there's a link to these in the resource section for this chapter as well. So the animations are well worth looking at because they explain how the bonds are formed. So as a consequence of these unequal sharing and the polarity of the bonds in water with these partial charges, it turns out that this gives rise to another type of bond. And in this case, it's the very weakest of all chemical bonds, called a hydrogen bond. And it's simply the attraction between a weak partial positive charge on a hydrogen on one water molecule and the weak partial negative charge on an adjacent water molecule. And because the oxygen has two partial negative charges, and each hydrogen has a positive charge, there are 4 of these partial charges, which means that water molecules can form 4 of these hydrogen bonds to 4 other water molecules. But what that also means is that each of these water molecules can form hydrogen bonds to 3 other water molecules, which can form hydrogen bonds to other water molecules, and so on. So basically, all water molecules are hydrogen bonded to each other. And it's the presence of these hydrogen bonds that explains the unique properties of water as a fundamental molecule for the existence of life as we know it. Water has a lot of interesting chemical and physical properties, and all of those relate to the fact that number one, water is a polar molecule because of the polar covalent bonds. And as a consequence of these weak charges related to the polar covalent bonds, you have hydrogen bonds between all the water molecules. And that changes everything. So the presence which we're going to see very shortly, because the next section and the last section of the chapter is all about the properties of water. So we actually springboard from this into looking at the properties of water. But before we do that, we need to talk about chemical reactions, and then we've got a short break, another concept check. So chemical reactions are simply about molecules interacting with each other to break the existing covalent bonds, because if we're talking about molecules, we're talking about covalent bonds. So when cells carry out chemical reactions, we've got molecules interacting with each other, breaking existing chemical bonds or covalent bonds and forming new covalent bonds. And if we draw a chemical reaction, I'm not sure whether I've got one. No, I don't have one there. So let me just put in a simple chemical reaction here. Yeah. So 2 hydrogen molecules plus an oxygen molecule gives 2 water molecules. And so if we were to diagram a hydrogen molecule, it would look like that. And an oxygen molecule diagrammed would look like that. And the water molecule diagrammed would look like that. And these lines simply represent covalent bonds, shared pairs of electrons. It's a way of diagramming a molecule and the covalent bonds in the molecule. So once we take a look at a hydrogen molecule, and remember we've got 2 of these, and we look at an oxygen molecule, we can see the existing covalent bonds between the atoms. And perhaps I should put in another hydrogen molecule here. And perhaps we can have another water molecule here, just to have the 2 water molecules on the other side. And if we add up the number of hydrogens here, which is 4, and we look at the number of hydrogens over here, which is 4, we've conserved all the hydrogens. They're present on both sides. If we look at the number of oxygens, which is 2, and we look at the number of oxygens over here, which is 2, we've conserved all the oxygen as well. What we had in the starting molecules, we wind up in the finishing molecules, or to use the right terms, what the atoms present in the reactants are the same atoms present in the products. What we've done, however, is broken these existing covalent bonds, and we've formed some new covalent bonds. That's what a chemical reaction is all about. So we have what is referred to as the law of conservation of matter. What we start with on one side of the chemical reaction, we finish up with on the other side of the chemical reaction in terms of the matter that's present, in terms of the atoms that are present. But we do rearrange it by breaking the existing covalent bonds and forming new covalent bonds. That's what a chemical reaction is all about. So this is also something that will become really important as we start to talk more deeply about chemical reactions in some upcoming chapters. More to come on that. So here is our concept check. Time for another little break and a concept check. So what type of bond is formed when 2 ions of opposite charge form a substance? And the strongest chemical bonds are what? And they're found in what? And occur when atoms do what? Really helpful question, isn't it? But we'll fill in the blanks. Let's take a quick pause. If you want to go take a bathroom break, grab a drink or something, pause the recording. If you want to pause the recording to think through the questions, see if you can come up with the answers, by all means do that. I'll stop for a few seconds and then I'll come back with the answers. So what type of bonds are formed between oppositely charged ions? Ionic bonds. And the strongest chemical bonds are covalent bonds and are found in molecules. When when atoms share pairs of electrons. So there are our answers to the questions. Now for the last section, talking about water and why water is important. So I hinted at this at the beginning, but water is really important, but it composes about 70% of our bodies. It really depends on the different types of organisms as how much water is present. So in our bodies, it's about 70%. In a jellyfish, it's about 80%. In lettuce or watermelon, it could be as much as 90 to 95%. At the other end, in a seed, the water level is down around 15% until such times as you rehydrate it and start the little seedling plant inside growing again. Because drying out the seed and taking all the water out, or most of the water out, puts the little seedling plant into a chemical stasis period. It's barely doing much chemistry at all, just enough to keep itself alive. But in order for it to start growing again, it needs more water. And so we expose the seeds to water. It's a process called imbibition. And by doing that, we rehydrate the little seedling and it starts growing again. So water is fundamental for life as we know it. And in fact, life began in water, and for the longest period of time, it remained living in water until around 500 million years ago, when life made its first tentative forays onto dry land in the form of plants. And ultimately, insects were the first animals to permanently colonize land, and then ultimately other animals followed them on shore, vertebrates that would give rise to terrestrial tetrapods and so on. But we still have a connection back to water, because you and I and every other organism on the planet begins our early embryonic development in an aqueous environment. We call ours the amniotic fluid inside the amniotic sac, which is true for most animals that we are familiar with, but some animals like frogs and toads, amphibians and so forth, still go back to the water for reproductive purposes, even though they may spend all of their adult life on dry land. So water is fundamental to everything about life as we know it. So why water? What is it about water that makes it so important? Well, one of the first reasons why water is so important, and perhaps this is something that we really ought to address here because it's not listed in this list, is that water is liquid. Over the largest range of temperatures of any substance that we know of. This is due and it's because water forms hydrogen bonds. That's it. And much of what we can say about the other chemical properties that are listed here as important properties of water come down to the fact that water forms hydrogen bonds, or that water is polar and can form hydrogen bonds. The two seem to go hand in hand. The fact that water is polar, that it forms hydrogen bonds, those are what influence the chemical properties of water and make it so absolutely unique, but also explain why it is so unique as far as life is concerned. How unique is it? bear in mind that the one thing that NASA always looks for before they even start to explore for the possibility of life is to look for the possibility of either water in its liquid state currently or water in its liquid state in the past. Because as far as we can tell, if you've got liquid water, irrespective of what sort of conditions exist, so long as the water is liquid, life will figure out a way of making use of that environment because liquid water is the key. And in some of the environments that we find life in here on our planet, we have to acknowledge that as bizarre as some of those environments seem to be, and as uninviting as those environments seem to be, as far as we're concerned, the fact that there is liquid water there means that some life form has figured out a way to take advantage of it. And it really does come down to that. So this is the reason why when NASA goes looking for life elsewhere, the first thing that they take into account is there liquid water there right now? Then there's the potential for life being there right now. Is there the possibility of liquid water being there in the past? Then there is the possibility of life being there in the past. Because our experience here on our planet, the only one that we have experience with, is that once the conditions for life to occur come into play, and so long as water is present in its liquid form, then life seems to be almost inevitable. In fact, you could say that life is inevitable. So long as there is liquid water. The other chemical conditions don't seem to matter all that much. So long as there is liquid water, life, as we know it at least, seems to be pretty much inevitable. So there is a very great likelihood of life elsewhere in the universe and certainly in our galaxy, and probably or possibly in our own solar system, because there are several really good places we could look where the conditions look very similar to conditions where we know life exists here on our planet. And it's quite possible that life has evolved multiple times, even within our own solar system. And NASA is, of course, going to go and take a look. We don't have time to really delve into that this morning or today, but we will perhaps talk about that maybe in the next chapter when we talk about the origin of life and the origin of organic molecules, because that becomes part of the next chapter. Anyway, let's take a look at these 4 important properties of water that have been identified. Cohesive nature of water, the ability of water to absorb huge amounts of heat energy without changing temperature very much, the fact that ice floats, something that is truly bizarre and weird and out of line with anything that a solid ought to do, because it ought to sink, and the fact that water makes a really outstanding solvent. So the idea of cohesion is really all about the fact that water molecules stick to each other. And in fact, they would rather stick to each other than stick to a whole lot of other things. And this is what is referred to as cohesion. Cohesion simply means that the water molecules stick to each other, and you can probably guess why they stick to each other, because of the hydrogen bonds. And so when we look for examples of cohesion, one that you might see, and you might recognize, is when you fill a glass partly full with water. Water doesn't form a flat surface, it actually forms a little curved region that goes up on each side of the surface. That's referred to as a meniscus. And that is water doing 2 things, because there is a parallel property that goes along with cohesion, which is called adhesion. Adhesion, water sticking to surfaces, and you can probably guess why it sticks to surfaces, because those surfaces have charge. So in part, the formation of the meniscus is because the water is sticking to to the glass because glass has charges on it. But as the water climbs up the glass, being attracted to those charges, it also pulls more water molecules out of the surface to form this curved region called the meniscus. So that's one situation where we see cohesion and adhesion, the parallel property. But here's another one. Again, if you take a glass and fill it to the brim, you know that if you very carefully add extra water, you can get it to actually fill above the edge of the glass. And what allows this to happen is surface tension. So surface tension is where the water molecules are sticking tightly to each other, more tightly than the force of gravity trying to pull them down over the side of the glass. And so long as there's not so much water that gravity wins because the weight of the water is greater than the surface tension, you can have this amount of water sitting above the level of the glass. But of course, if you add that one drop too many, you know that it all pours out because gravity always wins. So if you add that one drop too much of water, gravity wins and it pulls it out. Now, insects can take advantage of this because insects can take advantage of the surface tension and walk on water. I think that's mentioned on the next slide, but I want to put this in here in case I forgot to put it in. So we can also use the idea or acknowledge that cohesion and adhesion work together to allow trees to move water up. And again, we've got an animation that illustrates this. Again, you'll find this in the study area in Mastering Biology. And I'll make sure that the link to this is also present in the resource area of the module so that you can take a look at this. So you can see how cohesion and adhesion play a role in allowing trees to move water up the trunk and up into the leaves, a process that's called transpiration. And in fact, the great miracle here is that all the trees are using is the fact that water molecules are sticky and stick to each other and stick to surfaces. Whereas when we try and move water over the same distance as a tree, we have to use huge pumps and we may not even be able to move it in one continuous movement. We may have to do it in steps to move it over the same distance that trees are capable of moving it in one step, using the simple idea that water is sticky and it sticks to itself and sticks to surfaces, all by taking advantage of that. We don't seem to be able to take advantage of that over really long distances. Over short distances, not a problem. So when you suck on a straw, you're actually taking advantage of water's cohesiveness. Because as you suck the water up, the straw, you actually pull more water, because let's face it, soda and other things that you drink is basically water. So when you suck it up a straw, you're actually taking advantage of the cohesiveness of the water as well. So did I mention insects? Doesn't look like I mentioned insects, but I've mentioned surface tension. So again, surface tension is just the sticky nature of water to itself. Another thing that happens, again, because of the presence of hydrogen bonds, is that water can absorb a lot of heat energy and not raise in temperature very much. And the reason why is multifold, but one of the things that we need to remember here is that temperature So when you take the temperature of something, you're actually measuring the movement of the molecules. You're measuring kinetic energy, which is the energy of motion. So why do other hydrogen bonds change the way water responds when you add heat energy? Why doesn't the temperature go up immediately? Well, remember that each water molecule is hydrogen bonded to 4 other water molecules. And if you want the molecules to move, you've got to deal with those hydrogen bonds, because although hydrogen bonds may be weak, they're still there, and they prevent the water molecules from moving as fast as you might want them to, or as they might be able to. And so when you start adding heat energy, in order to get the water to increase in temperature, in other words, to get the water molecules to move faster, you've got to actually provide more energy, because you've got to take into account the requirement to break the hydrogen bonds. That's the reason why. And so it takes a huge amount of energy to move the water molecules, or to get them moving fast enough to break all of the hydrogen bonds, or even to have the ability to break them permanently, which is what happens when water starts to boil. In order for the water to boil and the water molecules to move away from each other permanently, in other words, for the hydrogen bonds to be permanently broken, you need to take into account all of the hydrogen bonds, and that can be a lot. That can be trillions upon trillions upon trillions upon trillions of water molecules, even in a small volume, like a typical bottle of water that you might buy from a snack machine. Even in a small bottle of water, even in the water at the bottom of the glass after you've had your drink, there are still going to be billions and trillions of hydrogen bonds, and it takes a huge amount of energy to overcome all of those hydrogen bonds, even though each hydrogen bond by itself is incredibly weak. So when you're dealing with really large volumes of water, like the ocean, it can soak up huge quantities of energy, heat energy, and really not change temperature much at all. And that has a cooling effect. So wherever you have land adjacent to large volumes of water, the land right up against the body of water is usually typically very cool. And we see that here in Florida, because we're surrounded by water on 3 sides. And so given that most of Florida is no more than 60 to 80 miles from the ocean, you don't have to go very far to see the effect of the ocean in terms of cooling. It's always much cooler along the coast than it is inland. And the reason why is because the land absorbs heat energy and then radiates it back and heats the air above the ground, which is what we're really talking about when we talk about the temperature for a day. We're talking about the temperature of the air, not the temperature of the land. And when we talk about the temperature at the coast, we're talking about the temperature of the air above the land and above the water, not the temperature of the land itself. Because the water absorbs all of that heat energy and doesn't radiate it back to heat the air, the temperature of the air above the ocean remains much cooler than the temperature of the air above the land. That's the reason why we have thunderstorms in the afternoon in summer. The cool air that comes in off the ocean pushes the hot air above the land up, and that's what triggers the thunderstorms every afternoon as the sea breezes come in. Now, I used to live in California, and I can tell you that we see the same thing in California. I used to actually live in the San Bernardino area, which is about 80 to 90 miles inland. And on a hot summer day, it could be close to 100 degrees in San Bernardino, but over in Los Angeles along the coast, it could be 75 to 78 degrees. And remember, the distance is only about 80 miles. And yet the temperature difference is somewhere around 25 degrees. What makes the difference in the temperatures? The fact that Los Angeles is on the coast and you've got the big body of water that is the Pacific Ocean, keeping everything cool. Inland in San Bernardino, it's all surrounded by the land and it heats the air above it and it gets quite hot very quickly. And again, we get sea breezes. And you can actually see it this time because you can see the sea breeze coming in because it brings all the pollution from Los Angeles. And so you can see the wall of pollution that comes from Los Angeles eastwards to San Bernardino every afternoon in summer. It was quite noticeable. You could stand and you could watch it coming and know that it was about to get really smoggy as the sea breeze brought the smog in from Los Angeles. I'm told that it's a lot better now. I left California in 1992 to come to Florida. So I'm told that it's a lot cleaner there now because they've dealt with the smog to some degree at least. But again, water can actually serve as a coolant. And we use that for our own body because not only does it take energy to raise the temperature of water to boiling point, it takes energy to convert it from boiling water to steam, and you have to add extra energy. So in order to get water to evaporate from your skin, it's got to change from liquid to vapor, and that means it's got to increase in temperature. That energy's got to come from somewhere. It comes out of your skin, and so we use evaporative cooling, sweating and evaporation, to cool our bodies down. But we've got to be careful here in Florida because the evaporation is a function of how humid it is. So we know that it gets really humid in summer in Florida, and the more humid it is, the less evaporation you get from your skin. So you've got to be very, very careful because if you can't evaporate the sweat very rapidly, if you get soaked in sweat but you don't get a lot of evaporation, you can still overheat because you're just sweating water, but you're not getting rid of the heat, and you become dehydrated because you're getting rid of that water, but it's not cooling you down. And so it's very easy to get heat prostration and heat stroke in Florida in summer when it gets really humid. If it's a lot drier, so if you go to the Southwest, to Texas, Arizona, New Mexico, even into California, it's a dry heat. It doesn't get terribly humid. And so evaporative cooling is actually a way of cooling air down as part of an air conditioning system. It's very effective as long as the water can evaporate. And if it's not terribly humid, then the water can evaporate. But if it gets too humid, then the water's not going to evaporate and you lose the cooling effect very rapidly. Again, one of the things that you know about water is that ice floats, so solid water floats on liquid water. That actually shouldn't happen because a solid is supposed to sink. A solid should always be more dense than the liquid. But in the case of ice, and somewhat uniquely in the case of ice, the solid is actually less dense. And the reason why is because the water molecules in ice are locked into place by the hydrogen bonds, and that those hydrogen bonds actually force the water molecules further apart than in liquid water at 4 degrees, the lowest temperature, degrees Celsius temperature, that water remains liquid. Below 4 degrees Celsius, water starts to freeze, and the water molecules start to get pushed further apart again as they get locked in by the hydrogen bonds to form ice crystals. So at 4 degrees Celsius, water molecules are really close to each other and water is extremely dense. But as it turns into ice, the water molecules are pushed further apart and the ice actually becomes less dense and the ice floats. And that's a good thing because the ice itself then insulates the cold water, it is at 4 degrees Celsius, from the freezing air above. And so the water doesn't freeze, and that allows life to continue to live in a frozen over pond and lake and even in the oceans where ice sits on top of the water. If ice behaved like a normal solid, it would sink to the bottom and the water at the top would then freeze and sink, and very quickly the water would become frozen all the way through. But because the ice forms an insulator and protects the cold water underneath from the freezing temperatures above, the water remains liquid. Yes, it's at 4 degrees Celsius. No, we would not like to live there. But at least it's liquid. And as I said, as long as the water is liquid, life is able to find a way to adapt and figure out how to live there. This is the reason why a moon around Saturn and a moon around Jupiter are of interest to NASA, because they've got ice over the top, but we know that there's liquid water underneath. The ice is really thick. In some cases, we think it's about 2 kilometers thick. But nonetheless, we know there's liquid water underneath. So liquid water under ice, we know life can exist there. So NASA is going to go and take a look. So there's potentially life elsewhere in our solar system as a consequence of this. So this diagram simply illustrates this idea of water molecules being really close together in liquid water at 4 degrees. So just so that we have an idea of what the temperatures are like. So 4 degrees C, the water is still liquid. The water molecules can still break the hydrogen bonds, but barely, but they can still do it. They're really close together in this case, however. Then when the hydrogen bonds get locked into place, as we lower the temperature even further, the water molecules are no longer able to break them. So the hydrogen bonds now lock them into place. We get an ice crystal, and you can see that the water molecules are actually further apart. And so ice is about 10% less dense than water at 4 degrees Celsius. So you've probably heard that one of the amazing things about an iceberg is that 90% of it is below the surface of the water, and I've actually made a note of that here on the slide. That's really actually looking at it from the wrong way, because it's not, the miracle is not that 90% of it is below the surface. The miracle is that even 10% of it is above the surface, because remember that a normal solid should sink to the bottom of the liquid. And so the really amazing thing about ice is that you can actually see it floating on the water, because it should, under normal circumstances, if water had regular chemical properties and not these unusual chemical properties because of the presence of the hydrogen bonds, if ice behaved like a regular solid, it ought to sink to the bottom and not be visible at all. So while people might say the amazing thing about an iceberg is that 90% of it is below the surface of the water, the really amazing thing is that even 10% of it is above the surface, because it shouldn't be there. But nonetheless, it's really important biologically, because it means that life can continue to live in lakes and the ocean where ice is floating on the surface, because it acts as an insulator and allows life to continue. Then the final really important property of water is that it acts as a solvent. And it acts as a solvent for those things that are themselves charged or polar. I think I've got something to that effect here. Okay, so I need to make some notes here for you, just to give you some technical terms to use. So water dissolves anything that is polar or charged. And the technical term is to say that these substances are hydrophobic. hydrophilic. So you can probably think examples of each of these. So something that would be hydrophilic, something that dissolves in water, would be something like salt or sugar. You can think of a whole range of things that dissolve in water. Anything that is hydrophobic fears water. I mean, hydrophilic means water loving. Hydro for water. Philic comes from the Greek word philos, which is a word for love. And so hydrophilic means water loving. Maybe I should put that in parentheses here. Water loving. And hydrophobic, well, you know what a phobia is. So this would be, let me erase the mistake here. Bring back the pen. So this would be water fearing. So those are the technical terms that are used here to describe the way water interacts with substances and the correct technical terms that we would apply to those substances. So the reason why we become really interested in water's ability to act as a solvent is because the chemistry of a cell takes place in water. So that's an important thing to remember. And this is something that we'll talk more about when we do chapter 5, the fact that, chapter 3, I'm thinking in for another class. It's chapter 5 here. In this class, it's chapter 3 when we talk about the organic molecules, the carbon-based molecules. What we're going to see is that they have special characteristics that make them hydrophilic, make them soluble, even though at first glance, it appears that they probably ought not to be. In fact, by the way they are constructed chemically, they actually take on properties that allow them to be soluble. So we'll talk in more detail about those in the next chapter, in chapter 3. So salts are extremely soluble by virtue of the fact that the ions, and in this case, we're talking about table salt, get surrounded by a layer of water. So the layer of water excuse me. So the sphere of hydration is simply this layer of water that forms around the individual ions and separates them from each other. And it's the ability to form this sphere of hydration that makes things soluble. If the water molecules can form this sphere, can form a layer of water molecules around whatever it is that's trying to dissolve, then it will be soluble. If it can't, then it won't be soluble. So if you try and mix fats with water, you know that they don't mix well, they separate out again, and that's because the water molecules are polar, but the fat molecules are non-polar, and so they don't mix together well. The reason why we use soaps and detergents is because soaps and detergents can interact both with the fats, because they are fats themselves, but they can also interact with the water because they've been chemically modified at one end to have a polar part that can interact with the water, while they have the non-polar fat part that can interact with the fats. And that allows the water molecules to interact with the fat globules and form a sphere of hydration that allows the fats to be floated off and dissolve, whereas without a detergent, not going to happen. So again, this is just a little trick to allow us to form a sphere of hydration around something that otherwise might not form a sphere of hydration. And it all comes down to being able to get things to interact with water and take advantage of water as a really good solvent. So that brings us to our last concept check. We've got one more property of water solutions to talk about, and then we will be done. So the last concept, well, actually there's a concept check at the end, at the very end of the presentation as well. So some insects can walk on the surface of water and ice floats. How can you explain these apparently unconnected properties of water? Let's stop for a minute. If you want to pause to think about this, go right ahead. I'll come back in shortly with the answer. So we can answer this question with two words: hydrogen bonds. And in fact, hydrogen bonds should be the first thing that comes to mind whenever you're asked about the chemical properties of water. So why can insects walk on the surface of water? Because water molecules stick to each other, they're cohesive. The idea of surface tension, the hydrogen bonds are, while individually very weak, when you've got lots and lots of hydrogen bonds, you create a very strong structure. And insects take advantage of that by spreading their weight out over the surface of the water so they don't break through the surface of the water. The hydrogen bonds between the water molecules are strong enough to support the weight of the insect if it gets spread out. Why does ice float? Again, it's hydrogen bonds. Remember, the hydrogen bonds lock the water molecules into position in the ice crystals and hold them farther apart than they would be in water at 40 degrees Celsius, the last time it remains liquid before it starts to freeze. And so the ice is less dense as a consequence of those hydrogen bonds, excuse me, and it floats on the liquid water. So it really does come down to hydrogen bonds. So obviously you couldn't just answer a question like this with hydrogen bonds, you'd have to be a little bit more detailed, but that would be the starting point of your thinking. So the final property of water-based solutions that we need to think about is the concept of pH. pH is a way of measuring hydrogen ion concentration in water-based solutions. And the reason why we have to think about that is because chemical reactions, and very particularly cellular chemical reactions, are very sensitive to the concentration of hydrogen ions. So when you have pure water, you do have hydrogen ions present. And that number of hydrogen ions is produced by breakdown of water. So water undergoes a process called dissociation, where the water molecules break down the hydrogen ions and hydroxide ions. and it's the hydrogen ions that we're interested in. And so in pure water, the number of hydrogen ions and hydroxide ions is equal. But when you start dissolving things into water, you can change the number of hydrogen ions. In fact, one of three things can happen. Nothing, you don't affect the amount of hydrogen ions at all, and it stays at a neutral situation, equal numbers of hydrogen ions and hydroxide ions. You can add hydrogen ions, you can increase the number of hydrogen ions, which means that you're making it acidic, or you can decrease the number of hydrogen ions, which means you're making it basic. So if you were to add something like salt, well, salt, when it breaks down, sodium chloride, table salt, that's not very neat. Sodium chloride breaks down to sodium ions and chloride ions, neither of which are hydrogen ions, so it has no effect. Something like HCl, otherwise known as hydrochloric acid, breaks down to hydrogen ions plus chloride ions. And so this is hydrochloric acid. And it's adding hydrogen ions, so it's increasing the amount of hydrogen ions. It's an acid. Something like sodium hydroxide breaks down to sodium ions and hydroxide ions. And this is a base. Now, the reason why it's considered to be a base is because if you add hydroxide ions, the hydrogen ion concentration has to go down. So let me put a note here. Adding OH minus decreases H plus. So if you add something in that is a hydroxide, like sodium hydroxide, that increases the number of hydroxide ions, you automatically decrease the amount of hydrogen ions, so you've got a base. So we use the pH scale as a way of measuring what happens when you dissolve things in water in terms of the number of hydrogen ions that are present. While that will also affect the number of hydroxide ions, it turns out that chemically, the hydroxide ions don't matter, only the hydrogen ions matter. So the pH scale, as it says here, runs from 0, most acidic, to 14, most basic. pH 7 is neutral, and that's the pH of pure water. So there's one more note here that is kind of important for you to understand. It says here the pH unit represents a 10-fold change in concentration of hydrogen ions. And the reason for that is that the pH scale is actually a stand-in or a substitute for what we know about the actual concentration of hydrogen ions. That's given as powers of 10. So we do talk about the pH scale in whole numbers and fractional numbers. But in fact, what we're really talking about is hydrogen ion concentrations as powers of 10. But we don't need to get into the detail. But what we do need to remember is that each time we move along the pH scale, one whole number pH unit, that actually represents a 10-fold change in hydrogen ion concentration. So one of the things that becomes confusing is if we go from a pH of 7, I'm going to move the text box again a little bit. So if we go from a pH of 7, back, pH 7 to pH 6, that's a 10 times increase. pH 7 to pH 5, which is 2 units of difference. You might think, well, that's 20, right? Well, actually, it's not. It's 10 times 10, or 100. So that's something that we need to remember. It can get really confusing. The other thing that's really confusing about the pH scale, and let me show you on the next slide because it gives you some ideas about the pH of some substances that you might be familiar with. Notice, and the way they've presented this here is good, but notice, because it actually pays attention to this, notice that as the pH numbers go down, the hydrogen ion concentration goes up. As the pH numbers go up, the hydrogen ion concentration goes down. So it's counterintuitive. It goes in the opposite direction to what you might expect. Bigger pH numbers, lower hydrogen ion concentration. Lower pH numbers, higher hydrogen ion concentration. So you need to make yourself aware of that as well. So the higher the pH, the lower the pH, the higher the hydrogen ion concentration. The higher the pH, the lower the hydrogen ion concentration. Can be confusing at times. So this diagram actually illustrates that again in a basic solution. Notice lower hydrogen ion concentration. So let me make this. So just reinforce this again as to what we mean by basic, neutral, and acidic. So acidic, high hydrogen ion concentration, neutral, equal amounts of hydrogen ions and hydroxide ions, basic, low hydrogen ion concentration. Then the other important idea that we need to be aware of here is the presence of chemicals called buffers. Buffers help, in the case of our body, various parts of our body to maintain a constant pH. So if it threatens to become too acidic, a buffer can take up hydrogen ions so that it doesn't become acidic. If it threatens to become basic, it can release hydrogen ions to stop that from happening. So it basically counteracts whatever effect may be happening. So if something is going to become acidic, increase in hydrogen ion concentration, the buffers soak up the hydrogen ions to stop that from happening. If it starts to become basic, there's a reduction in hydrogen ion concentration, then the buffer releases or adds back hydrogen ions to stop that from happening. And there are various compartments in our body, in our stomach, our small intestine, in our blood, where the pH is maintained at very specific values in order for the chemical processes that take place there to take place most effectively and most efficiently. And all trying to alter the pH in those locations is actually a not great thing to do, because it actually slows down the processes that are supposed to be happening there. So one of the things that you may have seen is alkaline water, bottled water that is supposed to have an alkaline pH. The problem with drinking alkaline water is that you alter the pH of the stomach from extremely acidic, and you can see that here, the stomach is around pH 2. If you raise the pH, bring it more to neutral by drinking alkaline water, what you're actually doing is preventing the successful digestion of proteins in the stomach, because that will only occur at pH 2 or close to pH 2. If you move it too far away from there by drinking alkaline water, for instance, or taking handfuls of antacids or other chemicals that can block the secretion of acid, you're actually doing yourself a disservice. You're not doing yourself a favor at all, because you're actually interfering with the beginning of the breakdown of protein. The stomach needs to be acidic in order to successfully begin the breakdown of protein. And you're denying yourself access to the breakdown of protein by neutralizing the acid in the stomach by drinking alkaline water or taking antacids or Pepsid or something like that on a regular basis, if it's not necessary. Now, periodically, it might be necessary if you have an acid stomach and you get heartburn, but that simply means that the little muscle that's supposed to close off the top of the stomach and prevent the acid contents of the stomach getting up into the esophagus, it can't do that. And the esophagus does not have the same protective layer that the stomach has. So the esophagus gets burnt, whereas the stomach never does, because it has a protective layer that protects it from the acid. And so it's meant to be acidic. The esophagus, not so much. The small intestine is meant to be at around pH 2, pH 8, and as the food passes out of the stomach into the small intestine, chemicals from the liver called bile salts that are stored in the gallbladder actually are mixed with the food to begin the breakdown of fat, but also to raise the pH from 2 to 8, so that the second part of the protein breakdown can occur in the small intestine at around pH 8, where it's intended to be. You don't want to mess with that, because then you start messing with your digestion and your successful access to the components of food that you need. As soon as you start interfering with the pH, you start interfering with the successful breakdown of food, and it can lead to all sorts of digestive issues. You should only really start playing with the pH if you are instructed to do so by your physician, and you actually follow the instructions of your physician, who hopefully understands the nature of what is wrong and how to fix it. Self-diagnosis and self-medication never work out well. It's typically a recipe for disaster. So just put that out there. We also know that the combination of carbon dioxide and water gives rise to a weak acid called carbonic acid. This is the reason why soda is partially the reason why soda is acidic. why anything that is carbonated, so sodas, beer, sparkling wines, anything that has natural carbon dioxide incorporated in it is acidic, mildly to moderately acidic because of the dissolved carbon dioxide. This carbonic acid is what etches its way through limestone to form caves. But when the ocean becomes acidic as a consequence of this, then corals and fish and mollusks, anything that needs to get calcium carbonate out of the water to form skeletons, to form the rocky part of a coral that surrounds the coral polyps, or the skeleton of a fish, or the hard shell of a mollusk or a snail or an oyster. The acidification of the ocean makes that so much harder. And in fact, it's leading to the die-off of corals and creating all sorts of issues. Coral reefs are actually under threat at this point. And so not only does carbon dioxide lead to increase in global temperature, global warming, but it also starts to change the chemistry of the ocean and makes it harder for the coral animals and the fish and the oysters and the clams and the snails and so forth that live in the ocean to successfully form their shells, which puts them at risk, and they are suffering as a consequence. And this is, again, part of understanding pH. The pH of the ocean is decreasing. It's becoming more acidic as a consequence of all of this. And this is us. This is what we're doing by putting carbon dioxide into the air. So it becomes an important part of what we need to understand about water solutions and the whole question of pH. Ocean water should be around pH 6.8 to around pH 6.5, but it's actually getting to pHs much lower than that as the carbon dioxide continues to dissolve into the water, and carbon dioxide is very soluble in water, unfortunately. So the oceans can no longer be considered to be a huge sponge soaking up heat energy and carbon dioxide without any consequences, because we are starting to see consequences now as more carbon dioxide gets dissolved in water and more heat energy gets absorbed into the oceans. The ocean temperature is rising, the pH is lowering, and that will not have good outcomes for life on our planet. So that is our foundations of chemistry. One more concept check before we close up for the day, close up for this chapter. So a solution with a pH of 5 has how many times more hydrogen ions per mil than a solution of pH 8? And what is this called? So if we look at this, there is a threefold change in pH. So it's a 3 pH unit difference. So 3 pH unit difference. And remember, each unit difference is a 10-fold difference, equal to 10 times 10 times 10 difference in H plus concentration. So 10 times 10 times 10 is 1,000. So it's 1,000 times difference. And anything that has a lower pH, pH 5 is lower than pH 8, and it's lower than 7, which is neutral, is an acid. So there's our last concept check for this chapter. I promised you that we would talk about radiation for at the end of the chapter as a tool. And here is the use of carbon-14 as a tool. We can use it to date fossils. Specifically, fossils that contain organic matter, organic molecules as a function of life. Because so long as you're alive, you are taking in food, and some of that food contains carbon, and some of that carbon is carbon-14. So you maintain a constant amount of carbon-14 in your body so long as you're alive. Once you die, however, you stop taking in carbon-14. Carbon-14, however, is radioactive, and so it slowly breaks down. And the way it breaks down is described as having a half-life. What does that mean? Well, it means that if you start out with 1 gram of carbon-14, at the end of one half-life, half of that gram is gone. So you're left with half a gram. Once 2 half-lives have passed, you've lost half of the original. Half of a half is a quarter. So after 2 half-lives, you've got a quarter of the original carbon-14 left. After 3 half-lives, you've got half of a half of a half, or 1/8 of what you started with. So what you need to know is how much carbon-14 is present in what you're trying to date, and how does that compare with the carbon-14 content of a living organism, currently living organism. Once you can figure out how much carbon-14 you've lost in your sample, you then can relate that to how many half-lives of carbon-14 have passed. And we know that 1 half-life of carbon-14 is approximately 5,700 years. So as soon as we know how many half-lives have passed, we multiply that by 5,700, and that tells us how old the fossil is. And that's useful for fossils that are up to around 80,000 years old, containing organic matter. Past that, the level of carbon-14 is so low that you really can't figure out how much carbon-14 is left, because there's not much carbon-14 to begin with. Once you've gone past about 80,000 years, the level of carbon-14 is so low that you can't do an accurate measurement. So you might ask, how do we date fossils that are older than 80,000 years? How do we do millions and billions of years? Because there are other radioactive isotopes that have a much longer half-life and allow us to date fossils back to almost the beginning of the Earth, about 4.5 billion years ago. So radioactive isotopes are not only useful in medicine, they're also useful in biology in tracing chemical reactions. They can also be used to date fossils, and there are a number of different radioactive isotopes that we use for that. Carbon-14 is just one, but it's the one that most people have heard about, and so that's the one that we talk about a lot. But you shouldn't think that carbon-14 is the answer to everything. It's not. It is limited as to how useful it can be used in terms of time that it can be used for, but we can use other radioactive isotopes that have longer half-lives that allow us to measure times going all the way back to very close to the beginning of the Earth 4.5 billion years ago. So that's another value for radioactive isotopes. So that's our foundational chapter for chemistry. We're going to build on this. I realize that it's a long chapter, a lot of foundational work here. That's why I've broken up into chunks with concept checks along the way. You can pause at any of those concept checks as you see fit. And hopefully you have, so that you've broken it up into smaller chunks. Next week, we'll start looking at the large biological molecules that are built out of carbon. We'll talk very quickly about why carbon is the basis for those molecules, and then we'll talk about the different types of carbon molecules that are found in cells. And there are 4 basic types, but more of that next time. Until then, if you have any comments, concerns, or questions about anything that we've discussed in this chapter, by all means, come and see me in office hours. I'll be more than happy to help you out. Send me an email if that's more convenient or you prefer to do that. But if it's a really elaborate question, or it might take a little bit of time to answer it, come to office hours. let's chat and let's make sure that we get any confusion taken care of. Till then, bye for now.